Niels Bohr was born on October 7, 1885, in Copenhagen, Denmark, into a family that epitomized intellectual achievement and Danish cultural values. His father, Christian Bohr, was a distinguished professor of physiology at the University of Copenhagen, renowned for his work on respiratory physiology. The Bohr effect, which describes how hemoglobin's oxygen-binding capacity changes with pH and carbon dioxide concentration, still bears his name in medical textbooks. His mother, Ellen Adler Bohr, came from a wealthy Jewish banking family prominent in Danish cultural and intellectual circles. The Bohr household was sophisticated, cosmopolitan, and intensely focused on education and achievement. Distinguished academics, artists, and intellectuals regularly gathered at the Bohr home for dinners where conversation ranged across science, philosophy, literature, and politics. Niels had a younger brother, Harold, who would become a distinguished mathematician. The two boys were extraordinarily close, competing fiercely in academics and athletics while supporting each other unconditionally. Both were brilliant students, both excelled at football, soccer, and both showed early signs of the exceptional intellectual abilities that would define their lives. But where Harold was precise, mathematical, and rigorous from an early age, Niels was more philosophical, more interested in the meaning and interpretation of ideas than in formal proofs. Even as a child, Niels would question everything, push ideas to their logical extremes, and refuse to accept answers that didn't fully satisfy him. His father encouraged this questioning nature, engaging young Niels in long discussions about scientific method, the nature of knowledge, and the relationship between theory and observation. Education in late 19th century Denmark was rigorous and classical. Niels attended the Gammelholm Latin School, where he studied not just science and mathematics, but also Latin, Greek, history, and literature. The Danish educational system valued breadth as well as depth, producing students who could think across disciplines. Niels thrived in this environment. He was an excellent student, not always the top of his class, but consistently strong across all subjects. But he was also athletic, playing football for his school and later for the Akademisk Bold Club, one of Copenhagen's leading clubs. Harold would eventually play for the Danish national team in the 1908 Olympics, winning a silver medal, while Niels was content to be a good club player, more interested in the teamwork and strategy than in individual glory. The turn of the 20th century was an extraordinary time for physics. In 1900, Max Planck introduced the quantum of energy to explain blackbody radiation. In 1905, Einstein published his revolutionary papers on the photoelectric effect, Brownian motion, and special relativity. Physics was being transformed from a science that seemed nearly complete, with just a few clouds on the horizon, as Lord Kelvin put it, into a field in crisis, where the most basic assumptions were being challenged. Niels Bohr entered the University of Copenhagen in 1903 to study physics and mathematics, arriving just as this revolution was beginning. He was 18 years old, curious, ambitious, and equipped with the intellectual tools to contribute to the transformation of physics. At the university, Bohr studied under Christian Christiansen, professor of physics, who recognized his students' exceptional abilities and encouraged him to pursue original research even as an undergraduate. For his master's thesis, completed in 1909, Bohr investigated the surface tension of water by studying vibrating jets, a complex problem involving fluid dynamics and precise measurement. The work was excellent, earning prizes and establishing Bohr as a serious experimental physicist, but it was his doctoral dissertation, completed in 1911, that showed the direction his thinking would take. The thesis was on the electron theory of metals, attempting to explain the properties of metals using the then-new ideas about electrons and atomic structure. Bohr showed that classical physics couldn't fully explain metallic behavior, quantum effects were necessary. The thesis anticipated many of the problems that would occupy him for the next several years. How do you reconcile classical and quantum physics? What are the limits of classical concepts when applied to atomic phenomena? How do you build a coherent theory when the old rules clearly don't work? In 1911, at age 25, with his PhD just completed, Bohr married Margrethe Norlund, whom he had known since childhood. Margrethe came from a distinguished academic family. Her father was a pharmacist and city councillor. The marriage would last until Bohr's death 51 years later and would produce 6 sons, 2 of whom would die tragically young. Margrethe was Bohr's partner in every sense. She managed his household, raised their children, served as his sounding board for ideas, and created the stable domestic foundation that allowed him to focus intensely on his work. She also became a gracious hostess, welcoming the stream of physicists from around the world who would visit Copenhagen in the coming decades, making them feel at home, managing Bohr's chaotic schedule, and ensuring that the atmosphere was conducive to the intense discussions and collaborations that would characterize the Copenhagen spirit. The same year he married, Bohr traveled to England to work with J. Thomson at Cambridge. Thomson had discovered the electron in 1897 and was the dominant figure in British physics. Bohr hoped to work with him on atomic structure, to discuss his doctoral work on electrons in metals, and to learn from the master. But the visit was a disappointment. Thomson wasn't particularly interested in Bohr's ideas, didn't engage deeply with his work, and seemed preoccupied with his own projects. Bohr felt frustrated and isolated at Cambridge, unable to make the connection he had hoped for. But then came an opportunity that would change everything: an invitation to visit Ernest Rutherford's laboratory at the University of Manchester. Ernest Rutherford was the opposite of Thomson in every way: boisterous where Thomson was reserved, collaborative where Thomson was distant, enthusiastic about new ideas where Thomson was protective of his own theories. Rutherford had recently discovered, through his famous gold foil experiment, that atoms had a tiny, dense nucleus containing all the positive charge and most of the mass, with electrons orbiting at relatively vast distances. The atom was mostly empty space. This nuclear model of the atom was revolutionary, but also deeply problematic. According to classical electromagnetic theory, orbiting electrons should radiate energy continuously and spiral into the nucleus in a fraction of a second. Atoms should be unstable, should collapse immediately. Yet obviously they didn't. Atoms were stable. How could this be explained? Bohr arrived in Manchester in March 1912 and immediately felt at home. Rutherford's lab was informal, energetic, filled with young researchers from around the world, all working on problems in atomic physics and radioactivity. Rutherford took an immediate liking to Bohr, recognizing his brilliance and his willingness to question fundamental assumptions. They would have intense discussions about atomic structure, about the nucleus, about how to reconcile Rutherford's nuclear model with the stability of atoms. Bohr absorbed the experimental details, the precision measurements, the careful reasoning from data, but he also brought his own philosophical approach, his insistence on finding the deep principles underlying the phenomena. In the summer of 1912, Bohr returned to Copenhagen to take up a position as assistant professor at the university, but he couldn't stop thinking about the problem of atomic structure. The Rutherford atom made no sense classically, yet atoms existed and were stable. Something fundamental was wrong with the classical picture. Then Bohr had a crucial insight. Perhaps electrons in atoms didn't obey classical physics at all. Perhaps they occupied only certain discrete orbits, with definite energies, and couldn't exist between these orbits. This was a quantum hypothesis, similar to Planck's quantization of energy in blackbody radiation, but applied now to atomic structure. If electrons could only occupy certain orbits, they couldn't spiral inward continuously. They could jump from one orbit to another, emitting or absorbing light in the process, but they couldn't radiate energy while remaining in a stable orbit. Working intensely through the fall of 1912 and winter of 1913, Bohr developed this idea into a complete theory. He started with the simplest atom, hydrogen, with just one electron orbiting a single proton. Using Planck's constant and a mixture of classical and quantum reasoning, he derived a formula for the allowed orbits. Only those orbits where the electron's angular momentum was an integer multiple of Planck's constant divided by 2 pi were permitted. From this, he could calculate the energy levels of hydrogen, the wavelengths of light emitted when electrons jumped between levels, and the size of the atom. When he compared his theoretical predictions with the experimental data on hydrogen's spectrum, the specific wavelengths of light that hydrogen atoms emit, the agreement was stunning. His formula reproduced the Balmer series, the Lyman series, the Paschen series, all the observed spectral lines of hydrogen, with remarkable precision. In July 1913, Bohr published his theory in 3 groundbreaking papers titled On the Constitution of Atoms and Molecules. The papers were revolutionary, introducing ideas that would transform physics: quantized energy levels in atoms, quantum jumps between levels, the correspondence principle, that quantum mechanics must reduce to classical mechanics in the appropriate limit, and a model that explained atomic spectra with unprecedented accuracy. The response from the physics community was mixed. Some, like Einstein, immediately recognized the importance of the work. Others were skeptical. Bohr's model was a strange hybrid of classical and quantum ideas, with ad hoc rules that seemed to work but weren't derived from deeper principles. It was, as critics noted, more a set of recipes than a fundamental theory. But it worked. And for the next 13 years, the Bohr model of the atom was the starting point for understanding atomic structure, even as physicists recognized it was incomplete. The success of the atomic model brought Bohr international recognition. He was invited to conferences, asked to lecture, consulted on problems in atomic physics. In 1916, at age 30, he was appointed professor of theoretical physics at the University of Copenhagen, a position created specifically for him. But Bohr had grander ambitions. He wanted to create an institute dedicated to theoretical physics, a place where researchers from around the world could come to work on the fundamental problems of quantum theory, where young physicists could be trained in the new physics, where the intellectual atmosphere would foster the kind of deep thinking and creative collaboration that he believed was necessary for scientific progress. He lobbied the Danish government, the Carlsberg Foundation, and private donors, arguing that Denmark should be at the forefront of the quantum revolution. In 1921, the Institute for Theoretical Physics, later renamed the Niels Bohr Institute, opened in Copenhagen with Bohr as its director. It was a modest building, but it would become the most important center for quantum physics in the world. Over the next 2 decades, nearly every major figure in quantum mechanics would spend time in Copenhagen: Heisenberg, Pauli, Dirac, Born, Schrödinger, and dozens of others. The Copenhagen spirit that developed there was unique. Informal, collaborative, intensely focused on conceptual issues rather than just mathematical techniques, characterized by long discussions where Bohr would push participants to question their assumptions and clarify their thinking. Bohr was not an easy person to work with. He thought slowly, spoke haltingly, revised constantly, and demanded that every statement be precisely formulated, but the atmosphere he created was extraordinarily productive. The early 1920s were a time of crisis in atomic physics. The Bohr model worked beautifully for hydrogen, but failed for more complex atoms. Attempts to extend it, to explain the spectra of helium, lithium, or heavier elements, ran into insurmountable difficulties. The model couldn't explain chemical bonding, couldn't account for the fine details of spectral lines, couldn't handle the effects of magnetic fields properly. It was clear that the Bohr model, however useful, was not the final theory. Something deeper was needed, a complete quantum mechanics that could handle any atomic system, not just hydrogen. The breakthrough came in 1925 when Werner Heisenberg, working in Copenhagen as Bohr's assistant, developed matrix mechanics, the first complete formulation of quantum mechanics. Heisenberg's approach was radical: abandon classical pictures of electron orbits entirely and work only with observable quantities like energy levels and transition frequencies. The mathematics was unfamiliar, matrices instead of ordinary functions, but it worked. It could calculate atomic spectra, handle complex atoms, and make predictions that agreed with experiment. Heisenberg had been deeply influenced by Bohr's emphasis on observables and on the limits of classical concepts, and matrix mechanics was in many ways the fulfillment of Bohr's philosophical approach. But Heisenberg's formulation wasn't the only one. In 1926, Erwin Schrödinger published his wave equation, a completely different approach based on treating electrons as waves rather than particles. Schrödinger's equation was more intuitive, used familiar mathematical techniques from classical wave theory, and gave the same results as Heisenberg's matrices. But the two formulations seemed conceptually incompatible. Heisenberg emphasized particles and discontinuous quantum jumps, while Schrödinger emphasized waves and continuous evolution. Which was right? Or were they both describing different aspects of a deeper reality? Bohr initially welcomed Schrödinger's work. The mathematical power of the wave equation was undeniable, and it provided tools for solving problems that were intractable with matrix mechanics. Schrödinger visited Copenhagen in 1926, and Bohr engaged him in intense discussions about the interpretation of the wave function. What did it represent? Was the electron really a wave, Or was the wave function just a mathematical tool for calculating probabilities? The discussions became heated. Schrödinger fell ill during the visit. Whether from the intensity of the arguments or from an actual illness is unclear, and Bohr reportedly followed him to his sick to continue the debate. Margaret had to intervene, insisting that Schrödinger be allowed to rest. These discussions were crucial in shaping what would become known as the Copenhagen interpretation of quantum mechanics. Bohr realized that neither the particle picture nor the wave picture was complete by itself. Quantum entities exhibited both particle-like and wave-like properties, depending on the experimental context. This was complementarity, one of Bohr's deepest insights. In some experiments, you see particle behavior, in others, wave behavior. Both descriptions are necessary for a complete understanding, but you can't observe both aspects simultaneously. The wave-particle duality wasn't a contradiction or a failure of theory. It was a fundamental feature of nature, revealing the limits of classical concepts when applied to the quantum realm. In 1927, Heisenberg, still working in Copenhagen, derived the uncertainty principle. You cannot simultaneously measure both the position and momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This wasn't a limitation of measurement technology, but a fundamental feature of quantum reality. Bohr immediately recognized the profound implications. The uncertainty principle, combined with complementarity, meant that the classical dream of a completely deterministic, fully knowable universe was impossible at the quantum level. There were fundamental limits to what could be known, not because of human ignorance, but because of the nature of reality itself. These ideas were presented and debated at the 1927 Solvay Conference in Brussels, where the founders of quantum mechanics gathered to discuss the interpretation of the theory they had created. The conference became famous for the debates between Bohr and Einstein. Einstein, who had contributed so much to quantum theory, was deeply uncomfortable with its probabilistic nature and with the Copenhagen interpretation. He presented thought experiments designed to show that quantum mechanics was incomplete, that there must be hidden variables determining outcomes, that God does not play dice with the universe. Bohr defended the Copenhagen interpretation, responding to each of Einstein's challenges, showing that quantum mechanics was consistent and that the apparent paradoxes arose from trying to apply classical concepts inappropriately. The Bohr-Einstein debates would continue for years, through correspondence and at subsequent conferences. Einstein kept proposing clever thought experiments, Bohr kept finding flaws in them or showing that they actually confirmed rather than refuted quantum mechanics. The debates were always respectful. The two men had deep admiration for each other, but they never reached agreement. Einstein died in 1955, still convinced that quantum mechanics, however successful, was incomplete. Bohr maintained, until his death in 1962, that the Copenhagen interpretation was the only consistent way to understand quantum phenomena. Modern experiments, particularly those testing Bell's inequalities, have generally supported Bohr's position, though the interpretation of quantum mechanics remains controversial even today. Through the late 1920s and 1930s, the Niels Bohr Institute became the undisputed center of theoretical physics. Young physicists from around the world competed for positions there, knowing that a year or two in Copenhagen under Bohr's guidance could make their careers. The atmosphere was unique. There were regular colloquia where visiting speakers presented their work, but the real physics happened in informal discussions, long conversations that could last for hours or days, where ideas were examined from every angle, criticized ruthlessly but constructively, and refined until they were as clear and precise as possible. Bohr's working method was notorious. He thought slowly and carefully, speaking in a low, mumbling voice with frequent pauses as he searched for exactly the right word or phrase. He would revise sentences repeatedly, trying different formulations, insisting that precision in language was essential for clarity in thought. Writing a paper with Bohr was an ordeal that could take months. He would dictate to an assistant, often a long-suffering graduate student, then revise extensively, then revise the revisions, then reconsider the entire approach and start over. Papers were published only when Bohr was completely satisfied that every statement was defensible and every ambiguity eliminated. This painstaking approach drove some collaborators to distraction, but it also ensured that work emerging from Copenhagen was of the highest quality. But Bohr wasn't just a demanding taskmaster. He was also warm, supportive, and genuinely interested in his students and colleagues as people. The institute had a family atmosphere. Bohr and Margaret would host parties and social gatherings where physics was discussed, but so was music, literature, art, and politics. Bohr loved detective stories and Western movies, would play ping pong with students, and enjoyed skiing and sailing. He believed that physics required not just intellectual brilliance, but also a certain playfulness, a willingness to imagine possibilities and question assumptions. The famous Bohr's horse joke, told in various versions, but always involving Bohr supposedly hanging a horseshoe over his door, for luck, and saying, "I don't believe in it, but I'm told it works whether you believe in it or not," captured his philosophical approach to concepts and their utility. The cast of characters who passed through Copenhagen in those years reads like a who's who of quantum physics. Heisenberg spent several crucial years there, developing his uncertainty principle and matrix mechanics under Bohr's guidance. Pauli came regularly, bringing his fierce critical intelligence and his famous phrase, "not even wrong," for theories that didn't even rise to the level where they could be evaluated. Dirac visited, impressing everyone with his mathematical brilliance and mysterious silence. Landau came from the Soviet Union, bringing news of developments in Russian physics. Gamow, Casimir, Kramers, Klein, Weisskopf, the list goes on. Dozens of physicists who would go on to make fundamental contributions to quantum mechanics, nuclear physics, and other fields, all spending formative time in Copenhagen, all influenced by Bohr's philosophical approach and by the collaborative spirit of the Institute. One of the most important relationships was between Bohr and Heisenberg. Heisenberg had come to Copenhagen in 1924 as a young postdoc and quickly became like a son to Bohr. They would take long walks together, discussing physics and philosophy, often late into the night. Bohr challenged Heisenberg to think more deeply about the meaning of his mathematics, while Heisenberg brought youth, energy, and mathematical virtuosity to problems Bohr posed. The relationship was sometimes tense. Heisenberg was more willing to accept mathematical formalism without complete physical understanding, while Bohr insisted on conceptual clarity, but it was also extraordinarily productive. The uncertainty principle, complementarity, and much of the Copenhagen interpretation emerged from their discussions and debates. Bohr's influence extended beyond quantum mechanics. In the 1930s, as physicists began to understand nuclear structure and nuclear reactions, Bohr made important contributions to nuclear physics. He proposed the compound nucleus model, explaining how nuclear reactions proceed. A projectile is absorbed by the nucleus, forming a highly excited compound state that then decays, emitting particles. This model explained many features of nuclear reactions and guided experimental work. Bohr also worked on nuclear fission, realized immediately after its discovery in 1938, and made predictions about which isotopes would undergo fission, predictions that would prove crucial for the later development of nuclear weapons and nuclear reactors. By the late 1930s, Bohr was not just a leading physicist, but an elder statesman of science. He had received the Nobel Prize in Physics in 1922 for his work on atomic structure. He was a member of numerous academies and scientific societies. He advised governments on science policy and education. He used his position to help Jewish physicists fleeing Nazi persecution, finding positions for them at the Institute or helping them secure positions elsewhere. When refugees arrived in Copenhagen, the Bohr home was often their first stop, with Margaret making them welcome and Niels working his networks to find them safety and employment. The rise of Nazism in Germany cast a dark shadow over European physics. Many of Bohr's colleagues and friends were Jewish or politically opposed to the Nazi regime. By the late 1930s, the exodus from Germany had become a flood, with physicists fleeing to Britain, America, Denmark, and other countries. Bohr's institute became a refuge for some, and Bohr himself worked tirelessly to help displaced scientists. He understood that the Nazis represented not just a political threat, but an assault on the values of international scientific cooperation and rational discourse that he held dear. When Germany occupied Denmark in April 1940, Bohr faced a difficult situation. Denmark was under Nazi control, but initially the occupation was relatively mild. The Danish government remained in place, and daily life continued with some semblance of normality. Bohr tried to continue his work, to maintain the institute, and to protect his colleagues and students as much as possible. But as the war progressed and Nazi policies became more oppressive, his position became increasingly untenable. In 1943, when the Nazis began rounding up Danish Jews for deportation, Bohr, whose mother was Jewish, making him partly Jewish under Nazi racial laws, was in grave danger. The Danish resistance, with help from the Swedish government, organized Bohr's escape. In September 1943, Bohr and his wife fled by boat to Sweden, a harrowing journey across the Øresund Strait. From Sweden, Bohr was flown to Britain in the bomb bay of a modified Mosquito aircraft. He was supposed to wear an oxygen mask, but failed to put it on properly and nearly lost consciousness during the high-altitude flight. It was a close call that emphasized how ill-suited Bohr, now 58 and accustomed to contemplative physics discussions, was to the dangers of wartime espionage. In Britain, Bohr was brought into the Manhattan Project, the Allied effort to develop an atomic bomb. His contributions were more advisory than technical. He didn't work on the detailed calculations of bomb design or uranium enrichment. Instead, he thought about the broader implications. Bohr immediately understood that nuclear weapons would change the world, that the post-war order would be shaped by who possessed these weapons and how they were controlled. He became concerned about a nuclear arms race, about the Soviet Union developing its own bomb, about the need for international control and openness about nuclear technology. Bohr traveled to Los Alamos in 1943 and 1944, where his presence was both inspiring and sometimes frustrating to the younger physicists actually building the bomb. His habit of speaking slowly and revising every sentence didn't fit the urgency of a wartime project. His philosophical approach to problems seemed too abstract for engineers trying to solve concrete technical challenges. Yet everyone recognized his brilliance and valued his insights. Oppenheimer said that Bohr made the enterprise seem hopeful, meaning that Bohr reminded them that they were doing something more than just building a weapon. They were potentially creating conditions for a more peaceful world, if the technology could be properly controlled. Bohr's main contribution during the war years was political rather than scientific. He met with Churchill and Roosevelt, trying to convince them that the atomic bomb should not be kept secret from the Soviet Union after the war. He argued that attempting to maintain a monopoly on nuclear weapons would inevitably fail. The physics was known, and the Soviets would develop their own bomb eventually. Better, Bohr argued, to share information openly, to establish international controls, to prevent a nuclear arms race before it started. It was a prescient vision of what would later become nuclear nonproliferation efforts. But his meetings with political leaders were largely unsuccessful. Churchill was unimpressed by Bohr. There's a famous account of their meeting where Churchill reportedly complained that Bohr spoke in a whisper about something I couldn't understand, and concluded he should be kept away from anything political. Roosevelt was more sympathetic, but also more concerned with maintaining American advantage. Bohr's proposals for openness and international control were noted but not acted upon. The Manhattan Project remained secret, the bomb was developed and used against Japan, and the nuclear arms race that Bohr feared began almost immediately after the war ended. The experience was disillusioning for Bohr. He had hoped that his scientific stature would give him influence in shaping the post-war nuclear order. Instead, he found himself on the margins, his advice noted but not heeded, his warnings about an arms race proven prescient but too late to prevent. Yet he continued to work on these issues for the rest of his life, writing open letters to the United Nations, advocating for international cooperation in nuclear matters, and using his Nobel Prize prestige to push for sanity in nuclear policy. After the war, Bohr returned to Copenhagen and to the Institute, which had survived the occupation relatively intact. The post-war years were difficult. Denmark was recovering from occupation, resources were scarce, and the physics community was trying to rebuild international cooperation after years of division. But Bohr threw himself back into work with characteristic energy. The Institute resumed its role as a center for theoretical physics, though now there were new centers competing for talent. Los Alamos, Berkeley, and other American institutions flush with funding from the atomic bomb project. Bohr's scientific work in these later years focused on quantum mechanics interpretation and applications, on nuclear physics, and on encouraging younger physicists. He never wavered in his commitment to the Copenhagen interpretation, even as alternative interpretations like Bohm's pilot wave theory were proposed. He continued to refine and defend complementarity, to argue that quantum mechanics required a fundamental rethinking of the relationship between observer and observed, and to insist that classical concepts had inherent limitations when applied to the quantum realm. His approach to physics remained deeply philosophical. Bohr was never satisfied with just getting the right answer mathematically. He wanted to understand what it meant, what it revealed about the nature of reality. This philosophical bent sometimes frustrated more pragmatic physicists who felt that if the calculations worked, that was enough. But it also inspired those who shared his conviction that physics was ultimately about understanding nature, not just predicting experimental results. His favorite phrase, repeated in countless discussions, was "It is wrong, it is not even wrong," adapted from Pauli but made famous by Bohr, meaning that some statements were so unclear they couldn't even be evaluated as true or false. In the 1950s, Bohr engaged in another series of exchanges with Einstein, now through letters and published articles rather than face-to-face debates. Einstein, Podolsky, and Rosen had published their famous EPR paper in 1935, arguing that quantum mechanics was incomplete because it led to spooky action at a distance, correlations between distant particles that seemed to violate locality. Bohr responded, arguing that the EPR argument relied on classical assumptions about separability and reality that didn't apply to quantum systems. The debate continued until Einstein's death in 1955, with neither man convincing the other. Modern experiments, particularly those by Elaine Aspect in the 1980s testing Bell's inequalities, have largely vindicated Bohr's position. Quantum mechanics really does involve non-local correlations, exactly as Bohr maintained and Einstein found so troubling. The spooky action at a distance is real, though it doesn't allow faster-than-light communication and doesn't violate relativity in the way Einstein feared. Bohr, who died before these experiments could be performed, would have found them profoundly satisfying, confirmation that his interpretation, however strange, captured genuine features of nature. Bohr's family life continued to be both a source of joy and profound tragedy. He and Margaret had 6 sons, Christian, Hans, Eric, Oj, Ernest, and Harold, named after Niels's brother. Christian drowned in a sailing accident in 1934 at age 18, a devastating loss that affected Bohr deeply. Harold died in childhood from meningitis, but the other 4 sons survived and prospered. Oj Bohr followed his father into physics and would win the Nobel Prize in Physics in 1975 for work on nuclear structure, making them one of the few father-son pairs to both receive Nobel Prizes in the same field. Bohr's last major public contribution was his open letter to the United Nations in 1950, in which he outlined his vision for international control of nuclear weapons and called for openness and cooperation between nations possessing atomic technology. The letter was largely ignored by policymakers, but represented Bohr's continued commitment to using science for peace and his conviction that the nuclear age required new ways of thinking about international relations and sovereignty. On November 18, 1962, Niels Bohr died of heart failure at his home in Copenhagen at age 77. He had been working on revisions to a paper until the day before his death, still refining ideas, still pushing for greater clarity and precision. The physics community mourned the loss of one of its giants. Tributes poured in from around the world, all emphasizing not just Bohr's scientific contributions, but his humanity, his dedication to international cooperation, his philosophical depth, and his role as a mentor to generations of physicists. Bohr's scientific legacy is immense and multifaceted. The Bohr model of the atom, while superseded by full quantum mechanics, remains the starting point for teaching atomic structure and is still used as a first approximation in many contexts. The concept of quantized energy levels, of quantum jumps between states, of the correspondence principle, these are now fundamental to physics and chemistry. Every time a chemistry student draws electron shells, every time a spectroscopist analyzes atomic spectra, every time a laser operates based on transitions between energy levels, Bohr's insights are being applied. But beyond specific scientific contributions, Bohr's greatest legacy may be the Copenhagen interpretation and the philosophical framework he developed for understanding quantum mechanics. Complementarity, the idea that contradictory classical descriptions can both be necessary for a complete understanding of quantum phenomena, has influenced not just physics, but also philosophy, psychology, and other fields. The insistence that measurement and observation play a fundamental role in quantum mechanics, that there are limits to what can be known simultaneously, that classical concepts have inherent limitations. These ideas, developed primarily by Bohr, have shaped how we think about the relationship between observer and observed, between knowledge and reality. The Copenhagen spirit, the emphasis on conceptual clarity, on rigorous examination of assumptions, on collaborative discussion and debate, influenced how theoretical physics was practiced. Many of the greatest physicists of the 20th century were shaped by time spent in Copenhagen, absorbing Bohr's approach to physics and carrying it with them to institutions around the world. The informal seminar style, the emphasis on thought experiments and careful analysis of measurement, the willingness to question fundamental assumptions, all bear Bohr's imprint. The Niels Bohr Institute itself continues as a leading center for physics research, still attracting students and researchers from around the world. In 1965, a new element was discovered and named bohrium element 107 in Bohr's honor, a rare recognition, as elements are usually named after places or mythological figures rather than individual scientists. The Niels Bohr Medal, awarded by the Danish Engineering Society, recognizes outstanding contributions to physics, and Bohr's face appeared on Danish currency, the 500 kroner note, from 1997 to 2011, perhaps the only theoretical physicist ever to appear on regular circulation money. The quantum revolution that Bohr helped create has transformed our world. The transistor, the laser, the LED, the MRI machine, the atomic clock enabling GPS all depend on quantum mechanics, on the understanding of atomic structure and quantum transitions that began with Bohr's 1913 papers. Modern electronics, computing, telecommunications, medical imaging all trace their origins to quantum physics. The economic value of industries based on quantum mechanics is estimated in the trillions of dollars. Yet when Bohr developed his atomic model, he was motivated purely by understanding, by the desire to explain why atoms were stable and why they produced the spectral lines that spectroscopists had observed. This encapsulates Bohr's approach to science, fundamental understanding pursued for its own sake, with confidence that practical applications would follow. He never worked on problems because they might be useful or commercially valuable. He worked on them because they were deep, because they challenged fundamental assumptions, because solving them would reveal something essential about nature. Yet the practical consequences of his work have been enormous, touching nearly every aspect of modern life. Bohr's political legacy is more mixed, but no less important. His efforts to promote international control of nuclear weapons failed in the short term. The arms race he feared began immediately after World War II and continues in modified form today. But his vision of international cooperation in science, of openness in nuclear matters, of the need for new ways of thinking about security in the atomic age. These ideas influenced the development of nuclear nonproliferation treaties, the International Atomic Energy Agency, and ongoing efforts to control nuclear weapons. He was ahead of his time, proposing in the 1940s and 1950s ideas that would only gain traction decades later. Perhaps most importantly, Bohr represented a certain ideal of the scientist. Deeply knowledgeable but humble, brilliant but willing to question his own ideas, ambitious for understanding but not for personal glory, committed to international cooperation and the free exchange of ideas, philosophical but grounded in experiment and observation. In an era when science was becoming increasingly specialized and compartmentalized, Bohr maintained a broad perspective, connecting physics to philosophy, politics, and human values. The atom on the Danish coat of arms, added in honor of Bohr's work, symbolizes his importance to Denmark, a small country that produced one of the giants of 20th century science. But Bohr never saw himself as representing Denmark alone. He was deeply Danish, loved his country, and took pride in Danish culture and values. But he was also profoundly international, believing that science transcended national boundaries, that the search for truth was a human endeavor that required cooperation across cultures and political systems. In the end, Niels Bohr gave us not just an understanding of atoms, but a way of thinking about nature that embraces paradox, that accepts the limits of classical concepts, that finds meaning in complementarity and uncertainty. He showed that the universe at its smallest scales is stranger than we imagined, that reality doesn't conform to our everyday intuitions, but that human reason can still comprehend it if we're willing to question our assumptions and think deeply about what our observations really tell us. The atom, once thought to be the indivisible building block of matter. The word atom comes from the Greek atomos, meaning uncuttable, revealed under Bohr's analysis to have a rich internal structure, a nucleus surrounded by electrons in quantized orbits, capable of absorbing and emitting light, participating in chemical reactions, and exhibiting both wave and particle properties. This revolution in understanding, begun with Bohr's 1913 papers and developed through decades of work by him and his colleagues, remains one of the greatest intellectual achievements of human civilization. When people look at the periodic table of elements, when students learn about electron shells and energy levels, when chemists predict molecular bonding, when physicists calculate quantum transitions, they are using ideas that trace back to Niels Bohr's insights about atomic structure. When philosophers debate the nature of reality and the role of the observer, when quantum computer scientists exploit superposition and entanglement, when cosmologists apply quantum mechanics to the early universe, they are building on the foundation Bohr helped create. Niels Bohr didn't just discover facts about atoms. He changed how we think about the relationship between theory and observation, between classical and quantum physics, between the observer and the observed. He created an institution that shaped generations of physicists and a philosophical framework that continues to guide our interpretation of quantum mechanics. He lived through 2 world wars, the development of nuclear weapons, and the beginning of the space age, always working to ensure that science served humanity rather than destroyed it. The boy who grew up in a cultured Copenhagen home, who played football and debated philosophy, who questioned everything and accepted no answer without deep understanding. That boy became the architect of our understanding of atomic structure, the father of complementarity, the conscience of nuclear physics, and one of the most influential scientists in history. The atoms that make up our bodies, the stars, the universe itself, we understand them better because Niels Bohr dedicated his life to asking the deepest questions and refusing to settle for superficial answers. That is his legacy, permanent.